The field of cosmology has divided itself into two pathways. One of these is guided strictly by data and description, the phenomenological approach. The other pathway is in search of an ultimate theory about the beginning and the end of the universe. Different scientists decide which route they want to pursue, but invariably these two paths cross each other. Cosmology today is a product of both data and theory. At this point, it is worth our while to summarize what we know about our universe based on the data and the theories of the past several decades. Once we have this in hand, and indeed we can simplify what we know into just 7 numbers about the universe, we can see how cosmologists speculate about its ultimate beginning and its very future. We first go back to the beginning. The question of the beginning has ancient roots, as we can discern from the ponderings of the Book of Job, composed probably 2,500 years ago. "Where is the way to the dwelling of light?" Job asks. "And as for darkness, where is the place thereof?" Today, our giant telescopes are like time machines that let us travel into the past. And looking back in time means looking far away. How far can we go? Let's start nearby. The Sun is 9 light minutes away. The nearest star is 4 light years distance. The center of our galaxy is 24,000 light years away. Andromeda is 2 million light years distance. The Andromeda galaxy is a naked eye object, though we need telescopes to get its distance. The most distant galaxy discovered to date was found with a combination of the world's largest telescopes on mountaintops in Chile and Hawaii. It is 12 billion light-years away. These telescopes have mirrors with diameters of 8 or 10 meters. They are big and expensive pieces of machinery, but provide the size necessary to collect enough light to see the most distant objects. By pushing back the frontiers of our exploration of the universe, we can understand our own planet in relationship to the largest scales of reality. We know, for example, that the Earth formed 4.6 billion years ago. We use the oldest rocks as fossils to date the Earth, and we use meteorites to date the solar system. We can see back even further. Our Milky Way galaxy formed 10 billion years ago, which corresponds to the ages of the oldest stars. The chemical abundances in these stars are primitive compared to those in our Sun. These stars are fossils that help us date the Milky Way itself. We can see back even further. We have discovered that the universe is expanding. Distant galaxies are rushing away from us. We also know that our planet, our Sun, and even our Milky Way galaxy are hardly at the center of things. Just imagine any point on the surface of an expanding balloon. This point, any point, is the center of a two-dimensional, expanding, curved surface. When the Earth formed, the universe was about 2/3 of its present size. When our galaxy formed, the universe was about 1/3 of its present size. The light from the most distant galaxy known was emitted when the universe was around 1/10 of its present size. Then galaxies were 10 times closer together. The night sky was full of galaxies. But this cannot go on indefinitely. In fact, we see fewer and fewer bright galaxies as we look even deeper. We knew this long before the age of the big telescopes. When observation fails us, we turn to theory. Theory tells us that galaxies cannot be ever present earlier and earlier, otherwise the night sky would be glowing with galaxy light. This is Olbers' paradox, named after German astronomer Heinrich Wilhelm Olbers in 1823. Olbers' paradox was known much earlier to Johannes Kepler in 1610 and described by English astronomer Edmund Halley and Swiss astronomer Jean-Philippe Loy de Chazeau in the 18th century. Even Edgar Allan Poe wrote about Olbers' paradox, and he even described the modern solution. Were the succession of stars endless, then the background of the sky would present us a uniform luminosity, like that displayed by the galaxy, since there could be absolutely no point in all that background at which would not exist a star. The only mode, therefore, in which, under such a state of affairs, we could comprehend the voids which our telescopes find in innumerable directions would be by supposing the distance of the invisible background so immense that no ray from it has yet been able to reach us at all. We infer that the galaxies, all of them, including those unseen, have a finite age. As we peer back in time, we must enter the Dark Ages, before there were any stars. But even the Dark Ages are not completely dark. There is a feeble glow in microwaves that comes from this period. Turn on your television. Put it out of tune to a channel that is not broadcasting. 1% of the fuzz on the screen is the glow from the Big Bang. One of the greatest scientific discoveries ever was the fossil radiation from the beginning of the universe. What else do we know? Thanks to the early astronomers, we know our universe is incredibly dynamic. Edwin Hubble discovered that the universe is expanding. He obtained galaxy distances and galaxy spectra. Redshifts measure velocity. The farther away a galaxy, the greater its speed. Modern data shows that the universe is expanding at a rate of 10 miles per second for every million light-years of distance. Now we can extrapolate back in time. The universe began 14 billion years ago. That in itself is a major conclusion, but there is more. Once, in the past, the universe was as dense as the sun. George Gamoff's great insight was to predict that it must also have been as hot as the sun in order for thermonuclear reactions to make the light elements. Helium makes up a third of the mass of all the matter in the universe. The helium was mostly produced in the Big Bang. The feeble residual glow of the Big Bang was discovered by serendipity the year before Gamoff died, and when his theory was long forgotten as well. That is science, the interaction of theory and data, even when theory is sidelined for a while. Gamoff's theory was confirmed by Arno Penzias and Robert Wilson, who were unaware of his ideas. They were radio astronomers mapping the Milky Way with a discarded telescope that was one of the first used for satellite communications. They discovered an excess microwave glow emanating from the whole sky. It was not of local origin. Bird droppings was one hypothesis that they quickly discarded, or terrestrial, or solar, or galactic. By a process of careful elimination, they found that the glow came from the universe. This was the fossil relic from the once fiery Big Bang. The universe around us was once 1,000th of its present size. This was the point in time at which the relic radiation came into visibility, 300,000 years after the beginning of the expansion. The universe became transparent. Before then, the universe was shrouded in a dense fog of radiation. Once, the universe was so dense and hot that even particles could not exist. This was a mere nanosecond after the Big Bang. Our current theory of particles is being tested by a consortium of scientists at CERN using the Large Hadron Collider. The gigantic machine might allow us to study the state of the universe as it was a trillionth of a second after the Big Bang. But cosmology does not stop there. When our machines reach a limit, we use theory. According to quantum theory, as used by cosmology, the universe began at a tiny fraction of a second. We can be precise. The universe began at 1,000th of a trillionth of a trillionth of a trillionth of a second after the Big Bang. Before then, we have no adequate theory, although we speculate in a later chapter on the ultimate beginning. At the incredibly high energies involved, the fundamental forces of nature are no longer distinct. The nuclear forces cannot be distinguished from the electromagnetic force. Only as the universe expands and cools to a lower energy state do these forces separate. There are two consequences of this cooling and separation of forces. One is that protons should even today be ever so slightly unstable. The process is very slow at today's low energies, but it must occur, if very rarely. Look at enough protons and one will decay before our eyes. Suppose a proton were to decay after 10 to the power of 20 years. This is around 3 times 10 to the power of 27 seconds. This would be the average lifetime of a proton. What this means is that some protons are decaying somewhere every second. Now, look at our own bodies. How would proton decay affect them? Our body contains something like 10 to the power of 29 protons. There would be something like 30 radioactive decays per second in our body. The proton decays into gamma rays, among other things. With so much irradiation on our body tissues, we would rapidly contract cancer. We infer that protons last at least 10 billion times the age of the universe. Otherwise, we all would be dropping dead of cancer. Proton decay is inevitable if the fundamental forces once were united. The weak and strong nuclear forces would then have been equal, and quarks freely formed and decayed. One can test the validity of the principle of grand unification by detecting proton decay today. An amazing experiment was developed to measure proton lifetimes. Take a vat of water containing at least 1,000,000 trillion molecules, or about 10 tons of water. Proton decay is statistical. It can happen any time. On the average, it takes a very long time. But in 10 tons of water, there would be a decay rate of around 1 proton per year if the proton lifetime were 1,000,000 trillion years. A proton decay is an energetic event producing gamma rays. These can be looked for. The current limit with experiments that monitor 50,000 tons of purified water is about 1,000 times longer. The first such prediction from the simplest model of proton decay has been tested and eliminated. It predicted that protons decay in 1,000,000 trillion years. If even 10 decays per year were measured, this would point to a proton lifetime that is 100 times longer, or around 10 to the power of 32 years, 10 to the power of 33 being the number of protons monitored in the experiment. This is where we might expect to find evidence if nature is sufficiently accommodating. The experiments are continuing. Another consequence of the application of grand unification theory is that we can understand how, when the universe cooled, it underwent a transition in phase from symmetry to asymmetry. This transition releases vast amounts of latent energy, much as when ice melts to water. The result is that the universe expanded dramatically, driven by this release of energy. This is the inflation we saw in Chapter 3. For a brief moment, the universe inflated enormously. We can now understand why the universe is so large. We also can understand why it is so uniform, relatively speaking. It looks the same everywhere. To imagine this, think of how a balloon gets smoother when it expands. And as a bonus, we even can understand the origin of the tiny fluctuations in density that seeded galaxy formation. They are relics of the quantum era. These earliest shifts in density are seen as temperature fluctuations in fossil radiation. We use the measurements of these fluctuations to run computer simulations to observe the effects of gravity as the universe expands. From an initially almost homogeneous distribution of density, structure is seen to develop. Regions with a slight excess in density accrete surrounding matter. The large-scale structure of the universe develops. Galaxies and galaxy clusters form. When it comes to telling this story of how the universe evolved, there is one slight complication. We don't yet know what dark matter is. What we can do is measure its existence. For example, our computer simulations are reliable for the development of the dark matter distribution. This is because only gravity is involved. Dark matter constitutes 90% of the matter distribution. But again, what is the actual dark matter particle made of? We think it probably consists of weakly interacting particles that can self-gravitate according to Newton-Einstein gravity. astronomers are beginning to map out the dark matter distribution by the technique of gravitational lensing. The dark matter clumps act like transparent lenses that bend light and distort the images of background galaxies. The simulated and observed maps of dark matter are in excellent agreement. So our assumption about what dark matter is cannot be too far from reality. Just 7 numbers. The universe seems highly complex, yet overall its cosmology is remarkably simple. It takes just 7 numbers to describe a model that fits all modern data. This includes all we know about the cosmic microwave background and the distribution of galaxies. Our first number is the age of the universe. This is determined to an accuracy of a few percent once we measure the rate of expansion. Our next 4 numbers are the densities of 4 important components of the universe. These are the densities of ordinary baryonic matter, of radiation, or photons, of dark matter, and of dark energy. Overall, we can directly map the densities of radiation and ordinary matter with telescope surveys that produce all-sky maps of galaxy distributions and the microwave background. In these sky maps, we measure the densities and the spatial variations from place to place. By reconstructing the surveys from the data in 2 dimensions, we can measure to the 3 dimensions we inhabit. What we don't see in this galaxy survey are the baryons that make up the intergalactic gas, the dominant home to baryons. But we can measure these too. We study the X-ray glow of the intergalactic plasma. We have 2 techniques for measuring dark components that dominate the density. One uses precise distance determinations, measuring the geometry of the universe, or equivalently the combined density of its various components. The other looks at the rate of growth of density fluctuations. Because dark energy is unchanging and dark matter is reduced in density as the universe expands, we can infer their densities. Our last 2 numbers are the values that controlled the seed density fluctuations from which all structure emerged. We arrive at this knowledge of structure by first taking the strength of the density fluctuations that are responsible for forming the galaxies. To this value, we add another important number, the spectral index that describes the distribution of the density fluctuations. That's an even 7. Armed with these 7 numbers, we go from the generality of Einstein's theory of gravitation to a model that gives a near-perfect fit to everything we know about the universe. Of course, assumptions are made en route. The most notable of these is that the universe is homogeneous and isotropic. That is, having both a smooth consistency and also seeming to have the same structure in all directions. But it is a great triumph of the theory that we can fit such diverse data with so simple a model. After all, there are thousands of independent data points that are needed to represent the matter and radiation distributions we observe, yet 7 numbers suffice. From this model, with its 7 numbers, we can predict the probable future of the universe. It is likely that its acceleration will continue forever. That at least is what the model tells us. In other words, this is what we can deduce from the data. There could be new data someday that might change our model, or there could be eventualities that are not foreseen in the simplicity of the model. Here is one possibility. The dark energy could spontaneously decay. In this case, the acceleration would be halted, but there is not a shred of observational evidence that leads us to this conjecture. Instead, we must face the forecast of continued acceleration of space, which means that within our horizon, or how far we can see with the largest telescope, there will be fewer and fewer galaxies. Today, the world's largest telescopes can map some 10 billion galaxies. But there will come a day, a trillion years or so in the future, when our horizon will span a single galaxy, our own. A lonely future beckons. Of course, by that time, the only stars remaining will be the dimmest of dwarfs. The initial hydrogen required to fuel fresh star formation will have been completely exhausted. However, There still will be the occasional flicker from stars self-destructing in supernova explosions. This occurs because pairs of white dwarfs can take immensely long times to spiral together before merging into the explosive mixture of a Type 1 supernova. This is 1 trillion years in the future. After this, there are no longer any stars capable of shining by nuclear energy. There is a feeble glow from the many white dwarfs which are becoming blacker and blacker as the final vestiges of gravitational energy are released. The universe is dark. It is full of stellar relics and smaller lumps of planetary mass. It will stay this way for a very long time. In fact, for about a number of years that equals 10 to the power of 33, or 1 billion trillion years. This is our best guess of the lifetime of a proton. The unification of the fundamental forces of nature requires that protons must be exposed to the radioactive decays that characterize the weak nuclear force. They are highly suppressed inside a proton, but if we wait long enough, decay is inevitable. That at least is what the simplest viable unification models of particles predict. At some point in time, possibly within 1 billion trillion years, the protons will decay. All that will be left in the universe are electrons, neutrinos, and photons. There will no longer be any structures. Nothing could exist that remotely resembled a planet. Life, in any imaginable form, would be over. Is the universe infinite? How can we tell whether the universe is finite or not? This has been a topic of great speculation. For example, 19th century English naturalist Thomas H. Huxley wrote, "The known is finite, the unknown is infinite." Intellectually, we stand on an islet in the midst of an illimitable ocean of inexplicability. Our business in every generation is to reclaim a little more land. When it comes to an infinite universe, our attempt to claim a bit more territory poses interesting issues. Anything could happen, and did happen. The writer T.H. White, applying his Arthurian theme, says simply that what is not limited may indeed happen. Everything not forbidden is compulsory, he writes. These ground rules provide a happy hunting ground in an infinite universe. First of all, what is infinite? Bigger than you can imagine. But we can never prove the universe is infinite. If it were truly infinite, there are some very strange contradictions that arise. There is another London or New York out there on a distant planet with identical inhabitants doing identical things, except that the weather is better. At its worst, there are infinite numbers of London cities. We may never access such wonders as may exist if they are beyond our horizon, present or future. It is more scientifically plausible to ask whether we could ever prove the converse, namely, that the universe is finite. On the grounds that an infinite universe is philosophically unappealing and quite possibly rather boring, let us compromise and consider that the universe is just very, very large. This is what we believe, and indeed, more to the point, what we measure. Hence, we have a nearly infinite universe. So how do we arrive at this conclusion? Cosmologists could find a signature that would point to a finite universe. There is an imprint of finiteness in the cosmic microwave background radiation. It disappears if the universe is too big, but it could someday provide a measure of finiteness. If the part of the universe that we observe is not special in any way, then the pattern of fluctuations we see in the radiation on the sky should extend to scales as large as the universe. This includes what we cannot see. You may wonder how we can measure what we cannot see, and of course we cannot. But we can measure the bits of such trajectories that lie within our horizon. Imagine coming across the steps to a place called heaven. Of course, you can't see this heaven, or even get to heaven without dying first, but the steps are there. So, one could measure accessible pieces of fluctuations that are, in their totality, invisible. And the absence of pieces in a finite universe would leave a distinguishing signature in the microwave sky. We haven't found such evidence yet, needless to say, although there are curious hints in the data that such an effect of finite size could exist. Better experiments are needed to study the tiny fluctuations in the temperature of the microwave sky. The universe is walking a fine line. According to our measurements, the universe is very, very close to being flat. The total mass of the universe keeps it at the critical point between being open, that is, expanding without limits, and closed, which means its space is curved and it will collapse back on itself. In a closed universe, gravity overcomes the expansion. But in an open one, the outward movement is stronger than gravity. What we find is that the universe is in a kind of balance between open and closed, even though, as we mentioned earlier, its flat space is expanding at an accelerated rate. The universe may be very slightly curved in an open or closed sense. This will turn out to be of interest when we discuss below whether the universe is infinite. What, then, is keeping the universe in balance so close to flatness, and what is causing the accelerated expansion? The answer may be dark energy. For a start, the visible matter that we find in the universe is only a third of the amount necessary to keep the universe in a balance between gravity and expansion. In a sequel to his early theory of general relativity, Einstein solved the imbalance by proposing that a cosmological constant, or force, counteracts gravity. This gave Einstein a static universe, a model that has now been discarded. As we saw in an earlier chapter, cosmologists Georges Lemaitre and Arthur Eddington revived the idea of the cosmological constant as the force that explains the expanding universe, and our current model is based on the Friedmann-Lemaitre theory of the Big Bang. Today, the modern interpretation of the cosmological constant is that it is energy with a negative pressure, a repulsive force that pushes outward. In contrast, positive pressure acts like gravity and exerts an attractive force, and this attraction curtails expansion of the universe. The repulsive force of negative pressure is like the tension in a string. It acts as a constant contribution to the energy density of the universe. If dark energy accounts for 2/3 of the universe's critical density, which we can't find in the matter itself, the flatness of the universe is explained. This theory has a remarkable consequence for how we picture the history of the universe. All energy densities decrease, bar one, that of dark energy, which is just the cosmological constant. At early epochs, the energy density of the cosmological constant would have been dominated by the density of ordinary matter and radiation. Its effect was negligible. However, at late epochs, the dark energy began to dominate. When the dark energy density is larger than the redshifting matter density, the universe enters into a phase of acceleration. This effect has been detected, thereby confirming the dominance of the dark energy. The modern Hubble diagram revealed a phenomenon that would have astonished Hubble. Supernovae in the most distant galaxies are found to be unexpectedly dim. The best explanation advanced to date is that the expansion of the universe is accelerating. The supernovae are farther away than would be the case in a non-accelerating universe. There are bizarre consequences. The future dominance of acceleration means that the number of visible galaxies is decreasing. Currently, we can see some 10 billion within our horizon. Someday in the far future, our Milky Way will be alone. Chasing supernovae. To understand how our universe may be accelerating by the force of dark energy, we need to measure distances of galaxies. For this, supernova stellar explosions are a key. As we saw earlier, supernovae are the events that seed the universe with heavy elements, allowing the evolution of stars and galaxies. But the brightness of their explosion also has turned out to be a remarkable tool for measuring distances. Fortunately, about half of all supernovae have the characteristics that allow for these measurements. Type 1a supernovae have characteristic spectra dominated by iron lines and are also more luminous than Type 2 supernovae. The latter are associated with the deaths of massive stars. Type 1a supernovae explode when white dwarfs, the relics of low-mass stars, accrete mass from or even merge with a companion and become unstable. Collapse occurs when the white dwarf is driven above the Chandrasekhar mass of about 7/10 of a solar mass. The energy released in the collapse is the source of the explosion. The explosion energy comes from the nuclear energy available when the carbon and oxygen of the white dwarf is burned into iron. The amount of nuclear energy is 10 to the power of 51 ergs, which is converted into light by the radioactive decay of nickel, which turns into iron. Thus we have a universal light source. A supernova at maximum light shines with the brilliance of 1 billion suns, brighter than many galaxies. Supernovae can be detected far away at a redshift of 1 or beyond, and provide the most powerful means of measuring distances to remote galaxies. Our only assumption is that a remote supernova of Type 1a shines with the same brilliance as a nearby one. Because its luminosity is determined by fundamental physics, this assumption is well-founded. In this way, supernovae were used to extend Hubble's diagram that plotted recession velocity of a distant galaxy against its distance. In 2000, cosmology was changed by a breakthrough in our understanding of how to best use supernovae to measure distances. Until then, supernovae had been our best method, but the accuracy of distance scales was relatively poor. There is an intrinsic range in supernova brightnesses, and without understanding this range completely, it was easy to arrive at large uncertainties. Then, in 2000, came the new discovery. Supernovae have a characteristic light curve, an exact rise and fall of luminosity. We found that the brighter the supernova, the slower it decayed. Now we had an empirical way of solving the distance uncertainty. Almost overnight, supernovae became a precision instrument for measuring distances to remote galaxies. This increase in precision led to the realization that the most distant supernovae were systematically dimmer than nearby ones. The accepted interpretation is that the universe has been accelerating. Hubble's diagram, in particular Hubble's law that velocity is proportional to distance, must be modified. It applies locally in the nearby universe, but as we peer farther away, a systematic increase in velocity is seen relative to what Hubble's law predicts. At a very large distance from us, the supernovae appear dimmer than they would be if the local Hubble law applied. This is acceleration. Because of the acceleration, the distant supernovae are farther away and appear dimmer. 2 dark energy puzzles. There are 2 immense puzzles about dark energy. Why is it just becoming important at the present epoch of the universe? A not unrelated but even greater enigma is this. Why is dark energy so small in energy density compared to expectations from the theory of the beginning of the universe? There is no explanation for the low value of the dark energy density. Any particle physics explanation prefers a value higher by 120 factors of 10. This yields the energy density at the Planck epoch, or the beginning of the universe in terms of classical physics. This energy is considered to be the most natural scale for dark energy. The discrepancy has led to a class of theories in which dark energy increases in density toward earlier epochs, depending on some power of the radiation density. In this kind of theoretical approach, dark energy is no longer the cosmological constant. At least, it is no longer constant. However, there is no compelling reason for this interpretation. Physicists love to generalize. One can introduce a new parameter, the ratio of the pressure to density of the dark energy. This parameter is conventionally called W. If Einstein's cosmological constant is the explanation for dark energy, W would be -1. However, acceleration only requires that W be less than -1/3. Much observational effort is going into determining the actual value of W and any possible redshift dependence. So far, all results point to Einstein's cosmological constant as being the dark energy. The hunt for dark energy. This hunt for dark energy will stretch our minds and generate ideas about giant new telescopes on Earth and in space. Ongoing and proposed experiments over the next decade are focusing on measuring dark energy by using several independent probes. No single technique may be good enough because there are always systematic errors. Some are known, but the most alarming are unknown. For different techniques, there are different sources of systematic error. Only by combining different techniques can one beat down on the systematics and improve the accuracy of the dark energy measurement. A political utterance by a former U.S. Defense Secretary, Donald Rumsfeld, in 2002 suggests the kind of exotic challenges involved. As we know, there are known knowns. There are things we know we know. We also know there are known unknowns. That is to say, we know there are some things we do not know. But there are also unknown unknowns, the ones we don't know we don't know. Fortunately, the measurement of dark energy is turning out to be like our understanding of musical sound. Primary among the new generation of experiments will be those seeking improvement in the measurements of baryon oscillations. These are the modern counterpart of the music of the spheres. The origin of the density fluctuations, predecessors of the galaxies, occurred in a coordinated way according to inflation theory. Any given scale formed at the same instant. Each scale had its own characteristic instant of creation as the spectrum of density fluctuations developed. Larger scales formed slightly later and were progressively smaller, which eventually triggered the bottom-up formation of cosmic structures. But the synchrony on each scale means that there is a regularity to be uncovered in the pattern of galaxy distribution. Random density fluctuations in air produce acoustic noise. Harmonization, such as obtained by playing a violin, produces music. As one studies the fluctuations in the distribution of galaxies, a pattern should emerge as the scale is increased. The fluctuations are not random. There is a natural frequency or wavelength in the cosmos that corresponds to the time when density fluctuations first began to grow stronger. The universe was for the first time becoming dominated by ordinary matter. The corresponding wavelength corresponds to the size of the horizon at this moment, or the distance light had traveled since the Big Bang, which turns out to be about 100 megaparsecs, the fundamental scale. There are also higher harmonics. Weaker fluctuations are expected at half the scale. This may seem far-fetched, but we have measured acoustic fluctuations in the cosmic microwave background. These are viewed at some 300,000 years after the Big Bang. The matter fluctuations must show a similar pattern. By viewing density fluctuations at a redshift of 1 in the galaxy distribution, we are probing the epoch of the universe when dark energy is beginning to be a dominant force. The natural wavelength is stretched by the effects of acceleration. Baryon oscillations provide a unique way of measuring acceleration and hence dark energy. Uncovering this pattern in the galaxy distribution involves surveys of thousands of square degrees to obtain redshifts of millions of galaxies. Redshifts are needed because they are used to extract distances by Hubble's law of expansion. In this way, one has a three-dimensional reconstruction of the universe. The volume surveyed extends to a redshift of 1 or beyond. This involves much telescope time, and the data acquisition challenge can be partly circumvented at a price if spectra are not obtained. A series of filters suffices to give a redshift at lower accuracy than is obtained spectroscopically. The ultimate experiment requires spectroscopy, essential for precise redshifts. Very large telescopes are needed in this case in order to extract spectra from the faint images of remote galaxies. Supernova hunting provides a kind of probe that is complementary to measuring redshifts. The light curves of a certain type of supernovae are universal. With enough supernovae, and millions will be needed, one can obtain more and more precise distance measurements. The idea is that with many galaxies at a redshift of 1 or even beyond, one can infer precise average distances at a given redshift. Even now, it is the difference between this luminosity-based distance and that inferred from Hubble's law that indicates that the universe is accelerating. But just how much is it accelerating? Acceleration is how one can measure dark energy, which need not necessarily be just Einstein's cosmological constant. If dark energy is dynamic, the universe might be accelerating less or more than the more naive assumption would predict. Astronomers have an embarrassment of riches when it comes to possible experiments that search for dark matter. We'll look at 3 of these. One promising method involves directly mapping dark matter. The basic principle is that gravity bends light. This is precisely the technique first employed to verify Einstein's theory of general relativity in 1919. Light rays from distant stars, passing near the edge of the Sun and observed during a total eclipse, were found to be bent by the Sun's gravity. The displacement measured amounted to a few seconds of arc. The same principle applies to light from remote galaxies passing through an intervening cluster of galaxies. The cluster is thought to be dominated by dark matter. There is enough dark matter to distort the light and modify the shapes of distant galaxies. The cluster acts like a transparent gravitational lens. The galaxy images are slightly elongated. The effect is small, but measuring thousands of galaxy images enables one to construct a map of the dark matter distribution. This has to be combined with another technique in order to get a handle on dark energy. A second approach is complementary and involves X-ray studies of galaxy clusters. One can measure the baryon content of clusters. In this way, the ratio of baryons to dark matter can be inferred. However, we already know what this ratio must be. The light element abundances were produced in the first minutes of the Big Bang. A successful explanation fixes the baryon abundance. One can, by combining the dark matter and baryon studies, infer the dark matter content of the universe. The result is that 1/3 of the total mass energy of the universe is in dark matter. The rest must be dark energy, or at least in the form of the cosmological constant. The cosmological constant is constant dark energy. A third approach measures something slightly different. Surveys are underway that count the numbers of clusters at different redshifts. Theory predicts that more and more massive clusters grow with time. Dark energy reduces the growth rate by countering gravity. There should be fewer clusters. Hence, cluster number counts are a probe of dark energy. Galaxy clusters can be counted by 4 independent techniques. One can perform deep galaxy surveys at optical wavelengths. These look for the overdensity of galaxies in a cluster. There are surveys of galaxy shapes that search for the slight distortions produced by gravitational lensing, the curvature of light rays as they pass through dark matter concentrations. These surveys are designed to measure galaxy image distortions for thousands or even millions of galaxies. One has to average more than hundreds of galaxy images to detect the tiny 1% image distortion produced by an intervening cloud of dark matter. A cluster of galaxies is seen as a region where the distortions are especially concentrated. X-ray surveys look for diffuse sources of X-rays emitted by the hot gas in a cluster. Finally, there are microwave surveys. These study the cosmic microwave background as seen through a cluster. The microwave photons scatter off the hot gas and gain energy, so the cluster leaves an apparent hole in the microwave background. All of these techniques have systematic limitations. There are the known unknowns and certainly the unknown unknowns. However, the systematics differ for the different techniques. We will progress by advancing simultaneously on all fronts and thereby beating the systematic errors. Nevertheless, using current telescopes, only a modest improvement in limits on the uncertainties in the amount of dark energy is expected in the next decade. A significant reduction in the uncertainties requires a major and expensive effort. New types of dedicated telescopes are needed. The projected costs are astronomical. One project involves building a spectrograph to simultaneously measure thousands of galaxy spectra using an 8-meter diameter telescope. The field of view on the Japanese Subaru 8-meter diameter telescope, intended to be used for this purpose, extends over a degree on the sky, or about twice the size of the full moon. This kind of optical telescope costs a modest amount compared to designs on a giant scale, such as a kilometer-diameter radio telescope. The construction of a telescope this large involves building an array of hundreds of smaller dishes. Spread out, this collective ensemble would have a collecting area equivalent to a square kilometer. Such an array is designed to simultaneously map thousands of square degrees in the sky. The discovery potential is thousands of times larger than any current telescope. In the near future, we look forward to the full operation of the square kilometer array, which will be located in a country in the lower southern hemisphere. Its aim will be to obtain spectroscopic redshifts in the 21-centimeter line of atomic hydrogen for nearly every gas-rich galaxy in the observable universe. By 2020, it is expected to have searched most of the sky to a redshift of about 1, when the universe was half its present size. Its projected cost is at least $1 billion. However, even these costs can be dwarfed by the potential costs of space telescopes. It is essential to go into space for measurement of infrared and X-rays from distant galaxies. The ultraviolet is also only attainable from space. One example of a successful space telescope that provided ultraviolet, optical, and near-infrared data on distant galaxies is the Hubble Space Telescope. One of its biggest advantages over ground-based telescopes is the precision of its images, which have up to 10 times higher angular resolution than is currently obtainable from the ground for faint galaxies. The Hubble Space Telescope has cost at least $5 billion. When initially contracted, it was for a price of $500 million. This sort of price inflation is common in space projects because of unexpected obstacles that often arise. In the case of Hubble, these included an optical defect in the original telescope that rendered out-of-focus images. This had to be corrected, and various cameras had to be replaced. Each repair mission requires a space shuttle flight and a dedicated team of trained astronauts. For pursuing dark energy, a large, new, space-based survey telescope will eventually be needed that is dedicated to one or more of the dark energy techniques we have described. These include hunting for supernovae, mapping dark matter with weak lensing, and evaluating the baryon wiggles. How constant is the cosmological constant? Ever since Einstein developed his ideas about the universe, the notion of a cosmological constant has been famous and much disputed. We still confront two major issues with the cosmological constant: its small value, which corresponds to a very weak force, and the fact that this force has only recently asserted itself in the history of the universe. First, why is the cosmological constant so small? A natural value of the vacuum density was attained when the universe last went through a phase transition. In fact, the quantum gravity theory tells us that there is more than one vacuum, but only one is truly empty, the true vacuum. As it cooled down from the quantum gravity regime, the universe spontaneously split into false vacua. These false vacua all have high energy fluctuations in terms of variations about zero. Our universe contains a true vacuum. The true vacuum has infinitesimal fluctuations that actually have been measured. But a false vacuum has other problems, and it is not a pleasant environment to be in. The false vacuum is a universe containing equal amounts of matter and antimatter, not a universe we would wish to inhabit. The true vacuum resembles our universe, predominantly made of matter. The transition between different states of matter occurred much as when a frozen lake melts and patches of ice remain for a while. The energy density predicted for the true vacuum, the one of our universe, is estimated from the energy at the time of the phase transition. It is higher by about 120 factors of 10 than the vacuum we inhabit. This is a major paradox. The small value is only the start of our puzzlement. Second, we find that the effect of the cosmological constant came late in cosmic history. The acceleration caused by the energy of the vacuum has only recently asserted itself. If it had happened much earlier, galaxies would never have formed. Why now? Physicists have no answer to these two profound questions: the small value of the cosmological constant and the epoch when acceleration began. There is a narrow zone of habitability. We have no theory of why Earth is in this zone. It just is. If it were not, we would not exist. Is the choice of the value of the cosmological constant any different from the coincidence of the Earth ending up as being habitable? Actually, it is. In the case of the Earth, we have somehow been selected out from many other planets to be habitable, thanks to the particular conditions found on the Earth. Some 300 extraterrestrial planets have been discovered. Almost all are hostile environments for life. So we know that there is a selection principle at work that stems from the physics of planet formation and the biology of the origin of life. The cosmological constant is very different. We are dealing with only one universe, not many. If we appeal to cosmic selection, then it follows that vast numbers of alternative universes must exist with different values of the cosmological constant. This could be the case. Many physicists are convinced that one can deduce the existence of a meta-universe from this line of reasoning. Others say it is hogwash, or more politely, a step too far. They prefer to wait for a new theory of physics that will provide a fundamental explanation for the observed value of the cosmological constant. This could well be the case. After all, physics can explain the mass of a star and even a galaxy in terms of fundamental constants. What it cannot yet do is explain the values of the fundamental constants themselves. In other words, how fundamental a constant is the cosmological constant? Is it even constant? Indeed, could it have changed over time? Astronomers are mounting experiments to look for possible changes in the cosmological constant as well as in the fundamental constants of nature. The results so far are not encouraging for any possible variation over time in the cosmological constant. All measurements point to Einstein's value, both today and in the past. However, there are hints that the fundamental constants of nature may have varied by small amounts. The data are controversial, as not all observers agree, but the essential argument is precise and well posed. The argument is based on certain atomic transitions in the spectra of quasars at high redshift. The wavelengths of some of these transitions depend on the fine structure constant. Others involve the ratio of electron to proton mass. By measuring these spectral lines and comparing them with results from laboratory spectroscopy, one can search for possible variations with time. There are terrestrial experiments that use natural radioactivity of long-lived isotopes to probe possible variations. The best known of these is an experiment that occurred in nature long ago. At a site in Africa that is naturally rich in uranium, an explosion occurred about 1 billion years ago. In 1972, a natural nuclear reactor was found in Western Africa in the Republic of Gabon by a French mining geologist while assaying samples for the Oklo uranium mine. The area was naturally loaded with uranium fuel by river sedimentation. The fissionable isotope uranium-235 was found to be depleted by amounts that could only be explained if it had been used up as fuel in a fission reaction about 1 billion years ago, when 235U, which has been decaying ever since, made up a much larger percentage of natural uranium than occurs today. Modern power reactors are artificially enriched to a similar level. Abnormally high amounts of fission isotopes were also found in nearby areas that can only be produced in thermonuclear explosions. By studying these rare isotopes, physicists are able to constrain possible variations in the fine structure constant over billions of years. To do better, one has to go into space by using distant galaxies or quasars. The lapsed time for light from remote objects in the universe is enormous, some 10 billion years. Over this timescale, one can be confident that these constants are the same to within 1/100%. But there are indications of possible variations at just below this level of sensitivity. If confirmed, this would be remarkable news. It would provide possible evidence for the existence of extra dimensions. The interface with our 4 dimensions would be subject to an infinitesimal leakage of information that could manifest itself as just such a tiny variation in the fundamental constants with time.